So thanks for having us. Happy to do this presentation. We'll be talking about scaling Bitcoin with zero-knowledge proofs, and in particular Starks, and few stuff like Mike mentioned, like Opcat and like clients using zero-knowledge proofs and so on. So first of all, we are actually seeing a lot of proofs in our daily lives, almost everywhere. One simple example is at the restaurant. We see proofs. For example, when you finish and you have the bill, you have the statement, which is what you have to pay. The prover in this context is the restaurant owner, and the verifier is the customer. And what you do in order to verify the amount is that you can recompute yourself and check that the sum is correct. So this is a form of proof, and this is checking the integrity of the statement by doing the re-execution. In this context, you are doing the same amount of work to verify than to do the proof. So it's not interesting in the context of scaling, but you have integrity with this model. Stark and zero-knowledge proofs, on the other hand, the idea is the same. You have a claim, a statement, and that can be anything, and you have the prover that will produce the proof and the verifier. The difference is that the integrity is not provided by re-execution, but via math. And we'll try to see how it works in a nutshell. But before talking about how it works, those are the important properties that Stark in particular have. You can use Stark for privacy, which is the zero-knowledge aspect of it. So some inputs of the prover can be shielded. So you have a notion of private inputs and public inputs. For us on StarkNet, so StarkNet is the layer 2 that we are building currently on Ethereum, but we plan to expand on Bitcoin. Currently, we are using Stark proofs mostly exclusively for the scaling aspect, not for the privacy aspect for the moment. But we can do that with Stark, and we know how to do that, and we support it. We want to support it with our proving stack. So you can have privacy with Starks. Our focus is mostly, as I said, on scalability. Stark give you the very interesting property that it's exponentially faster to verify the proof than doing the re-execution of the statement of the program, which is a very interesting property. So with respect to the size of the computation, so the bigger the computation, the bigger the gap between the verification time and the computation time is, which is very interesting scaling properties, because usually it's the opposite. The more work you do, the harder it is to verify. But here it's more interesting as you batch more computation, which is a quite interesting property for scaling. Also, they are universal, so they are applicable to general computation. They are also transparent, which means that there is no need for a trusted setup or a ceremony. There are some systems like Snarks, for example, that require a trusted setup, a ceremony where participants will contribute to some randomness, entropy for the system, and you need at least one honest participant for the system to be secure. So Starks are very interesting because you don't need that. It's transparent, so it's a universal. It's applicable to general computation, and it's transparent. Another very cool aspect of Starks is that they are very lean and using battle-tested cryptography. In fact, they are relying mostly on hash-based system. So they are very simple in comparison to elliptic curve pairing zero-knowledge proof systems. And in addition to being more simple, they are also post-quantum secure, which is also some interesting property that they have. So this general idea originated from the PCP theorem. And there is one sentence in the paper that is super interesting, which is a single reliable PC can monitor the operation of a herd of supercomputers with powerful but unreliable software and untested hardware. So the idea was that a single computer could be able to verify the integrity of a bunch of super powerful computers. Back in the days, it was only theory; it was not practical. But this was really the inception of this idea of doing integrity via maths. So the intuition behind the PCP theorem. So you can generalize it like this. You start with a state hash X, and after running a number of transactions, for example, 1 million. Yes, there is a difference between Starks and ZK Starks. In fact, yeah, this is what I said. So you can use Starks for both the scaling and privacy, but here we use it mostly for scaling. So technically, yes, we should say ZK Starks when you use the actual ZK, but here I'm mixing the terms, so I'm just saying Starks for simplicity. But yeah. Would you say that the difference between verifier and proving runtime could also contribute? Yes. Okay, I see what you mean. Yeah. For example, the fact that the prover has to do much more work. Yes, of course, you need to have some mechanism. So, for example, in the context of StarkNet, you need to pay to submit transactions. So it's like a regular blockchain. You need to pay fee to submit transactions, and of course, the amount of computation that the prover will do should be properly accounted in the transaction fees. But it's not easy because there are multiple entities in the system when you build, for example, a ZK rollup. I will touch it a bit later, but it's not an easy problem, but it's correct, yes. So this is you execute a number of transactions. Okay, this need to be bounded, otherwise you can solve the halting problem and then you can win an award. So this has to be bounded. So here it's an arbitrary number, but of course, when you generate a proof, it has to be bounded. And then after executing a certain program, you reach a new state. Okay, this is the general statement. And this is applicable to any program, in fact. So it looks like a pseudo-like set of constraints. You can see it like that, like the prover will basically submit the solution of the Sudoku, and the verifier will sample a single constraint. And by doing that, you can verify the validity of the constraint, like according to the Sudoku rules. But the interesting property is that sampling the constraints takes exponentially small time in comparison to checking the whole solution and generating the whole solution. Then a good proof satisfies all constraints. This is what is called completeness. It means that for every true statement, you are able to generate a proof. And a proof of a false claim satisfies less than 1% of the constraints. So this is the soundness aspect. This is the ability to forge malicious proof. Of course, you want this number to be as close to 0 as possible, and you can play with the numbers. For example, the number of queries and so on, because when you multiply the queries, you reduce the probability of being able to forge a malicious proof. Yes, so then the verifier can conceptually post another random puzzle. The prover will submit the solution, and again, the verifier will sample and check a single constraint. So this is the general idea. So with the PCP, as I said, it was impractical. It was just the theory. So it took a bunch of years and decades and papers and new breakthrough up to make it actually practical. So I will skip all the breakthroughs and paper, but the last one, which is the invention of Starks, that this was the first time when it was actually practical at a large scale, at a very large scale, and something that could be doable in production. So this is the general idea of the Stark protocol. You have a statement, a program that you want to prove. You basically have the first step that is called the arithmetization. You need to convert this program into something that can be used in the Stark protocol, which is polynomial constraints over a finite field. So it's everything is modular arithmetic in the Stark protocol. So there is this step of arithmetization that is you take a program, Fibonacci, whatever, and you convert it to a set of polynomial constraints, and then you commit the polynomial with some hashes and Merkle trees, and then you have some different steps like Fry to test the low degree of a polynomial, and Fiat-Shamir. Fiat-Shamir is used to make the protocol non-interactive. I forgot to mention, but the Stark protocol is completely non-interactive. So you have, when we say prover and verifier, they don't have to actually interact with each other for the different queries and so on. And this is thanks to Fiat-Shamir, because conceptually in the protocol, you need some interactivity. Because the verifier, as I said, will have to do multiple queries in order to detect a malicious prover. But of course, we don't want interactivity. It's easier if you don't have it. So Fiat-Shamir is used to actually simulate some random oracle. And the basic idea is that because the prover needs to execute the whole program here, and generate the execution trace. So the execution trace is a witness of the whole execution of the program. You can see it as a big giant table with some columns, which are the parameters of the program or the state. And each row is the values of those parameters after different execution steps. So the prover has to generate, to run all the program, generate the execution trace, then commit to it with a Merkle commitment. And the idea of Fiat-Shamir is that you will reuse the hash of the next round as a query, as the input of the verifier for the next one. It means that you cannot cheat, otherwise you have to do the whole execution and the whole rerun the whole program execution trace and so on. So you have to do a lot of work if you want to cheat, and you have to multiply that with the number of queries. So this is how you simulate a random oracle model using Fiat-Shamir. Okay, now let's go to how we can combine Starks and Bitcoin. And surprisingly, the idea of Bitcoin is quite similar to what was written in the PCP theorem. Is the main difference is that the consensus and the verification of integrity is done via execution, and this is how you come to consensus, because all the nodes re-execute all transactions, and this is how you can verify the integrity of computation. So before Bitcoin, we had only like centralized systems with trusted party. So you have to trust basically a central party for the integrity of the system, and you depend on the honesty of the central party. And the idea of blockchains and Bitcoin in particular is that you have inclusive accountability. It means that anyone can verify the integrity of the system by re-executing transactions. And with Stark proofs, this is a new way of verifying the integrity without re-executing the transactions. So you have the transactions, you have the prover that will execute them and generate the proof. And then the verifiers, that can be anyone, any node on the network or whatever, they just have to verify the proof, and then they are convinced that the result of the computation is correct. So if the computation is taking some transactions applied to a state and having a new state, then you can verify the integrity of the new state after applying those transactions, but without executing the transactions. Instead, you will just verify the proof, and at the end, you get the same result as if you had re-executed the transactions. Okay. Of course, it's not new, but just to compare how it's done on Bitcoin and on Ethereum. In the case of building a ZK rollup using Stark proofs, if you want to inherit the security of the layer 1 and settle on it, there are some differences that make it more challenging for us to do it on Bitcoin in comparison to Ethereum, for example, and I will explain why. On Bitcoin, there is actually no state. The only notion of states is the UTXO set, so this is the state. As opposed to Ethereum, where there is a global state with smart contracts and EOA, so accounts that are controlled by private keys. And for an account, you can have some logic, some code, and each smart contract can have its own state, and it's global, meaning you can interact between different smart contracts. So in order to be able to implement a verifier on Bitcoin, because ultimately this is what you need to do if you want to be able to settle on Bitcoin. Settling meaning sending those proofs that we saw before, verify them on chain, and only then update the state of your layer 2. This is how you can inherit the security properties of the L1. In order to do that, we need a few elements. The problem with the Bitcoin state, so the UTXO, is that changing the state is based on knowledge only. So anyone that knows how to unlock locking script or UTXO can do whatever they want with the state. They decide the next locking script for the UTXO. So in fact, it's the equivalent of changing the logic of a smart contract. So if you want to implement an equivalent of Bitcoin smart contracts, you need two things. You need a persistent logic and state. Logic as in the code of the program itself, and the ability to control how the state and logic is updated on chain. This is what you need to have. So surprisingly, Opcat could help to achieve that, and we will see how. So of course, Opcat, you all know, it's a simple opcode that take two elements on the stack, concatenate them. It was disabled very early, etc. But that you already know. How Opcat can help to implement a Stark verifier. First of all, it can help for the notion of a state because it actually enables covenants, and we'll see why. And also, it can enable efficient Stark proof verification. Mainly because in the Stark protocol, we have to do a lot of Merkle tree verification and so on. So having this primitive that concatenate two elements together is very practical for verifying Merkle tree. And interestingly, so as I said, the Stark protocol operates over a finite field. It's modular arithmetic. So the first generation of prover that we have, originally from the Stark paper in 2018, uses 252 bits field elements, which is big for a Bitcoin script arithmetic. But the good news is that there was some new breakthrough after the Stark protocol, something called Circle Stark, which is some new breakthrough that makes Starks even more efficient and so on. And the cool thing is that this new prover that we are working on operates over a much smaller field. It's called Mersenne31 prime, and it's a 31 bits field element, which is very nice because Bitcoin script has 32 bits arithmetic, so it fits very well. So it was a nice coincidence that makes it even more interesting for us to implement the verifier. Okay, then Opcat can help to have a state and a Stark verification. So hence you can imagine to implement smart contracts. And because you can have a Stark verification, maybe you can build an L2 with that. So covenants, the idea of covenants, of course, is to get introspection and to for a transaction to have the ability to know about the context in which it's running and to be able to do different stuff based on the inputs, outputs, and stuff like that. So there is something called the Schnorr trick that was discovered by Andrew Polstra, and there is a blog post, an article that describes it. But basically, the idea is that with opt-checksig and cat, you can emulate opt-tails hash, which is another covenant proposal. And the idea is that you will send the hint, what we call hint, as transaction data, and then with this Schnorr trick, you can do the introspection and use it in a Bitcoin script. So this is how the Schnorr trick works. But basically, you play with some parameters, and then at the end, what you get is that the signature is the equivalent of the transaction hash +1. And then it means that you are able to rebuild the transaction from the PCs, and this is why you need opcat. And then you are able to validate the signature, and then you can use that as a way to build covenants, basically. Okay, so now how would it look like to implement a smart contract on Bitcoin? So you would basically split the logic and the state. So the logic would be the actual code of the smart contract, and you would represent it as a pay-to-taproot address. And for the state, you could use, for example, a pay-to-witness script hash. And then you would use basically the introspection that you can have with opcat to be able to enforce that the logic is consistent. And how can you do that? Simply by verifying that you have an output here that corresponds to this one. And here you know that the logic of the program has not changed. The script, the UTXO, will still be locked by the same program, which was the first condition, being able to verify the consistency of the logic. And then because of the introspection, you are able to restrict how the state can be changed. So here, to be clear, by state, I mean the actual state of the program. So we'll see an example. So it's not a representation of the state, it's the state itself, the data. So for example, if you want to implement an on-chain counter, which is of course a meaningless example, but it's just to illustrate the idea. In the state, you would put the value of the counter itself, so the state data. And
so it means that it cannot be some kind of Merkle root. It has to be the state.
No. Yeah, this is the naive way to do that. It's not the good way to do that. Yes, okay, later we will see that actually you can do better.
Okay,
yes,
okay.
Exactly.
Thank you.
This is the next part. Yeah, exactly. Of course, you don't want to do that because for a simple program, it's cool. But if you want to implement like a big state or whatever, you cannot. Yeah. But it's better to understand the concept. So here, again, the first thing you do is verifying that the transaction output includes the same logic. This is how you verify that the logic of the smart contract is persistent. And then you can simply verify that the output difference is 1. And this is how you can implement an on-chain counter as a smart contract on Bitcoin if you have opcat or something that gives you covenant. Okay, now you can do better, of course. So as Adrien said, of course, you don't want to put the state. So here, instead, you put the state root, and you can decide how you want to do the representation of the state. So usually, it's just a Merkle root. You represent your state as a Merkle root. For example, this is exactly what we do with StarkNet as a layer 2. With all the accounts in smart contract that we have on StarkNet, we Merkleize the whole state of StarkNet, and then on-chain, on the verifier, we can put only the state root. And with that, and the verification of the proof, you can verify the integrity of the whole state. So the first difference is that indeed you put the state root and not the state directly. And the second difference is that the logic of the contract won't be the actual logic of the program, but the verification of the proof of the computation that you want to check. Yeah, you mentioned the proof can be quantum safe. In this structure, does that work? Or could the funds be redeemed by the taproot we pass bypassing the quantum resistance? Very good question. Unfortunately, yes, the problem with Taproot is that you can always tweak a public key that can spend. So yes, we will be right in this case as well. So this is actually a very big problem because we believe that Slack proofs can be very interesting to help for quantum resistance for Bitcoin, but because of this issue in Taproot, indeed, this is a big problem. We don't know how to solve it for the moment. Yeah, good point. Yes, yeah, you would verify the Stark proof and not the computation itself. You will not execute the computation on chain, but just the verification. And then it becomes very interesting because first of all, for those who ever built a program in Bitcoin script, you know how painful it is. It's really non-trivial to build some complex logic in Bitcoin script, and it was a feature, not a bug. Okay, and also it's quite error prone, and it's hard to make it secure. So if for every smart contract you will do the first model, this one, it means that you would have like to implement complex Bitcoin script logic, and it's very error prone, it's complex, and it can be insecure. So in this model, you have one program, which is the verification of the proof, and you can do like a bunch of audits. You can like really take the time to make it secure and have a lot of people working on it, etc. But when it's deployed and well audited and so on, you don't have to rewrite it each time you want to implement some new logic, because the verification of the stack proof will stay the same, no matter what program the stack proof is actually representing as computation. Another cool aspect is that you can write then your smart contract with higher level languages that are much more developer friendly and less error prone and so on. Here in the context of our stack, you will do that in Cairo, which is the language we specifically created to generate provable programs and to generate efficient stack proofs. I will touch a bit later about it. But there are other options. Some people are, for example, implementing RISC-V compatible proving systems, also using Starks, different flavor of Starks. So it's different trade-offs. I will touch it a bit later. But the idea is that we went with the most performant, efficient way, which of course has some trade-offs because you need to implement in a new language. So where if you use a proving system that supports Rust, you could reuse existing Rust program. Technically, there are a lot of caveats here, but we can discuss about it later. And yes, and then you can save cost and have scaling properties because of that if you build an L2 with it, and we'll touch a bit also on this. A lot of like concerns of people when it comes to OPCAT discussion and stuff like that is that it will bring like stuff that we don't want on Bitcoin. This is why I wanted to talk also about the benefits for Bitcoin itself as money, because of course I am in the fix the money first camp, and I believe that it's by far the most important mission, and it should be like of course the focus of Bitcoin. But I believe that this model can be actually beneficial. So first of all, the obvious one is scaling, because you can offload computation to layer 2s while inheriting the security of Bitcoin. There are different trade-offs, and we can discuss and debate about what inheriting security properties of Bitcoin means and what it will take for some people to consider that you actually have the same properties. It's an interesting topic. But yes, this is the first benefit. You can have scaling, both in terms of throughput, but also in terms of cheap fees. Then, as I said before, safety, simplicity, in the sense that you can write the logic of the programs in a higher level language instead of Bitcoin scripts. So if you want like new flavor of multisigs or vaults, etc. So really like monetary use cases, you can do that in more developer-friendly way. Also, with this system, you can imagine to have better UX for users that will interact with the layer 2s, because then you can have systems like account abstraction. This is something that we have, for example, on StarkNet. The idea is basically that every account is a smart contract, and you can implement whatever logic to authenticate with your account. It means that you can, for example, implement Face ID authentication. It's not a theoretical example. It exists. So we have some wallets that are actually using that. So the users don't even have to have a seed phrase or anything like that. So it can be interesting for normies, for which it can be complex sometimes. And still, you can imagine to have like, of course, some recovery features and stuff like that, like social recovery wallet and everything you want. So it can also be interesting in the context of UX and privacy. Initially, I also added quantum resistance, but because what we said before, it's not clear for the moment how you will do that, at least not with taproots. So maybe there are other ways. We are actually exploring different options, but for the moment, nothing concrete. But yeah, privacy also can be interesting, because you can implement privacy using the ZK property. So privacy on the layer 2. Some challenges, concerns, stuff that come back a lot when it comes to the OPCAT discussions. As I said, the last one, which is that it can enable undesirable use cases. So it's a broad debate discussion, and probably now even more, like with the current op return drama, and what we consider as spam or not is apparently very controversial. So I won't go into that, but this is one of the concern or pushbacks or challenge that we can see when there are some discussions about OPCAT. The first one is about security, unknown unknowns. I think this one is a bit tricky, because it's the same for any upgrade, in my opinion. But yeah, I agree we need more research on this front, for sure. And then MEV. Some people are worried that this could bring some MEV and centralization forces and so on. So we started a research fund to start thinking more in depth about all those things, security, economics, MEV, whatever. So if anyone is interested, you can have more information on the website. And the idea is really, to be clear, it's not a fund that is only for people that are pro-OPCAT, not at all. It's really about having more buying power and people thinking about it. So if you are against OPCAT, it's very good, actually, if you can do some research about that. And so the fund is really for pro, cons, neutral opinions, but yeah, for serious and deep research about some topics. Yes, just briefly, something to mention. Imagine a world where we can actually verify stack proofs on Bitcoin L1, then we can build ZK Rollups and so on. There is still something that is not fully solved, which is data availability. The concept of data availability is, if you want to really inherit the security properties of the L1, you want a way where people can actually reconstruct the state of the layer 2 by only relying on the security of the layer 1. So by data availability, concretely what we do, for example, in the context of StarkNet that settles on Ethereum, when we submit a proof on the layer 1, there is the on-chain verification smart contract. We send not only the proof, but also the state diff between the previous state that was verified, that is written on the L1, and the new state after executing and verifying the new proof. So you have one state. You imagine you settle once every 8 hours. So this is arbitrary, by the way. You can decide the logic you want for your ZK rollup. For example, what we do, we have a logic where it's either after a certain time or after we batch sufficient activity. The intuition here why we do that is simply because you want it to be interesting to batch a lot of computation before settling on the L1. The more you wait, the more you batch computation because of the property I mentioned at the beginning. It's exponentially more interesting. So the more you batch computation, the better. But of course, the trade-off is finality. So the more you wait, the more the actual L1 finality will be longer. So those are trade-offs, and you can play with them in your system. But okay, imagine you settle once every 8 hours. So you have a state, which is the state of your layer 2. Then 8 hours later, you have batched billions of transactions, whatever. You generate one single proof. You send it to the on-chain contract, and you send also the state diff, which is how you compute the new state from the previous one. Different ZK Rollups are doing different techniques here. There are mostly two families. The first one that I mentioned, which is state diffs, and the second one is compressed transaction data. We strongly believe, and I think we demonstrated already after a few years on mainnet, that state diff is more optimized and more efficient than sending transaction data. Anyway, so data availability means the ability to be able to send those state diffs to the L1 so that anyone can reconstruct the state of the layer 2 if needed. For example, if the operators of the layer 2 are withholding the data and so on, you are still able to reconstruct the state of the layer 2. Because even, let's say you have a system with unilateral exit and stuff like that, in order to use it, you need to have a view of the actual state of the layer 2. And this is what the data availability solves. On Ethereum, it's easy because literally Ethereum implemented the separate mechanism for data availability. I don't know if you are familiar, but this is what is called blobs or the donk sharding on Ethereum. And the idea is that you have blocks for transactions and stuff like that, and you have another peer-to-peer network on the consensus that is used to send those blobs of arbitrary data that usually layer 2s are using, like all different layer 2s are using that. The interesting aspect here is that there is a separate fee market for blobs, which is interesting because it means that, let's say you have a lot of congestion on the L1 in terms of transactions. This spike of transactions won't impact the price of blobs and vice versa, which is good, for example, because if, let's say, you have a bunch of L2s that are submitting a lot of data to the L1, there will be a congestion on blobs, but it won't affect users that just want to interact on the layer 1 and they don't want to deal with the layer 2s because the free market is separate. Anyway, it's just how it works on Ethereum. Of course, on Bitcoin, this does not exist. So this is also a challenge to solve in the future if we see a world with the ZK Rollups on Bitcoin. So I did some simulation based on some data that we actually consume on Starknet mainnet when we settle on Ethereum. So it will represent approximately a throughput of 230 TPS on Bitcoin. Maybe you think it's a low number, or maybe it's a high number. I think it's already a good improvement in terms of scaling. Because we are talking about 200 TPS constant and with like sub-cent transaction. So it can be still an interesting scaling factor, but I want to be clear that this is still a challenge for in the future. Won't go into the details, but we have different solutions with different trade-offs. There is something called Validium. The idea is that you can use off-chain data, and there is also something called Volition, which is hybrid mechanism. The idea would be to give the optionality for application developers to choose the DA layer, whether it's on-chain or off-chain, depending on the security level they want for some part of the state. Anyway, it's a bit complex, but yes, DA will be something, a challenge also in the future for Bitcoin layer 2s. Okay.
Maybe we can just, if anyone has any questions, maybe we can pause for a few seconds here to allow, if anyone has any question on everything we have talked about so far. There is a lot of data, and I know that Abdel and I are working with that like every day, but maybe there are some areas you want us to go deeper into. So feel free to ask in the chat or just open the mic.
Yeah, and feel free to interrupt me if you want.
Just a clarifying question. You mentioned on one of the slides, I think it was smart contracts and proofs slide. You talked about higher level languages, and this technology can be used for things other than StarkWare's layer 2, like I think you mentioned vaults, multi-sig privacy. I'm just trying to tease out StarkNet from what you're providing here. Like, what you're talking about here is sort of a set of tools and toolkit that you've worked on that StarkNet could use, assuming some changes in Bitcoin, but this isn't like StarkNet specific.
No, absolutely. Okay. It's not, absolutely. A good point. Yeah, maybe it was not clear. So thank you for jumping on that. No, absolutely. Those primitives are completely like generic, and by the way, all this technology is open source, so it can be used in the context of StarkNet, but of course you can use it completely outside of StarkNet. And in fact, I will touch later few examples that are completely unrelated to StarkNet that are using exactly those infrastructure primitives. Yes, exactly. So StarkNet is just one showcase of what you can do with that as scaling layer 2 with zero knowledge proofs, but yeah, you can do much more, and it doesn't have to do anything with StarkNet, to be clear.
Thank you.
Okay.
For example, maybe one construct that few people might be familiar with is more like if you want to scale Bitcoin just to have another more like UTXO-based layer 2, this would also be possible. Like you can restrain. You don't have to have a general purpose VM as a layer 2 to be proven and verified by Bitcoin. You can design your layer 2 in such a way that you could only do payments, for example, right?
Yeah.
So it would have consequences on like the scaling factor, because the weight of the transaction would be different. To prove it could be more efficient, less efficient, etc. But really, the way you expand Bitcoin here is completely, it's free to be designed. So StarkNet is just the easy example because it's in prod, it works. So we use it, but we have designed StarkNet with the goal of being general purpose. We could as well say that because we can verify Stark proof on Bitcoin, we will design a layer 2 just to do payments. And it can be kind of UTXO based, right? And I know that some construct like shielded CSV could benefit from that construct. So again, this is the realm of possibility is very large.
Yeah, and even broader than that, it does not even have to be a layer 2. Again, I will touch few examples that are absolutely not on chain, that don't even require a soft fork to be used in the context of Bitcoin ecosystem. Yes. So StarkNet is an example of general purpose layer 2. Adrien said that you can also do UTXO based payment only layer 2, but you can also use Stark proofs completely outside the context of layer 2 and even outside the context of blockchain. In fact, we strongly believe that ZK in general will it's a completely new paradigm. Like having the ability to verify integrity using math only is 0 to 1 in itself, so it will affect a lot of different industries in the future. It just starts with blockchain because this is the only industry where people are sufficiently paranoid and they care about trustlessness that there are incentives to actually use ZK, but it will affect other places, I'm sure. Okay, so maybe I will touch the other examples before doing the demo. The demo is very fast, but maybe I will talk about the other use cases before and jump back to the demo if we have time. Okay. Some exploration projects that we are doing that are completely unrelated to what we discussed. I will detail a bit more two of them. We are doing explorations on the Cashu protocol using StarkWare, building also some like Bitcoin-like clients using our stack. And also we are doing some exploration on Nostr, and I will explain. Can we sync a Bitcoin node in a minute? Maybe with StarkWare. So we discussed about Star protocols and so on. I want to illustrate with this use case that it's tangible. You can use efficient tools to generate those proofs. It's not only mood math, you can code with it and in a quite developer-friendly manner. So initially generating star proofs was a big deal. It's really something complex because for any program you need to do the arithmetization, writing polynomial constraints. It's a nightmare. It's very complex. Very few people in the world literally can do it. I cannot. I could not. It was very painful. So interestingly, Cairo originated from the fact that engineers, as you know, are lazy, and it's good. So instead, they did not want to do those this manual work by hand, and because it was super complex. So they started to think, okay, if you want an analogy, writing star proofs before the invention of Cairo was about building ASICs for any programs. You need to wire every program into like some polynomial constraints and so on. And Cairo, the engineers, they had this idea, okay, maybe we can actually build something that will be like a CPU. And this is Cairo. This is how Cairo was invented. And interestingly, Elie Ben Sasson, who is the inventor of Starks, he was very skeptical. He told to the engineer, oh, it will never work. It's impossible to do that. And they managed to do that. And surprisingly, not only they were able to do that, but it was in many cases even more efficient than the manual writing of those polynomial constraints, surprisingly. Anyway, so as I said, we specifically designed Cairo to be able to generate star proofs. So it's a language that is designed to be provable. It gives you the guarantee that if you write a program in Cairo, you will have the ability to generate an efficient star proof to prove. Unlike some other solutions that I mentioned before, like RISC-V-based system and so on, what they are trying to do, and it's the same with ZK VMs, they try to find ways to make existing dev infrastructure provable. But in the process, of course, there is huge overhead because those systems, like RISC-V, instruction set, and so on, of course, was not designed to be ZK-friendly. By ZK-friendly, it means that Cairo, the language and the VM, is designed at its core to be ZK-friendly. Like all operations on the Cairo VM already operates on the finite field of the prover, which is something that you don't have with the existing system. So you need to emulate all the modular arithmetic logic for all the basic operations, addition, whatever. So the overhead is huge. So I won't go into the details, but this is why Cairo was invented. And then StarkWare realized that it was so powerful that it could be something to actually develop as a public good infrastructure that we use internally for StarkNet and other stuff, but also that can be used by anyone to write provable program that use the power of StarkProofs. So a use case that we are implementing with that, maybe some of you are familiar with the Zerosync. So this is exactly the same idea. And in fact, Zerosync was actually written in Cairo. The main difference between Zerosync and this new project that we are doing now, there are two main differences. The first one is that Zerosync was developed in Cairo 0, which was the first version of Cairo, which was way more low level and Pythonic and stuff like that. The new version of Cairo is way higher level and it's very Rust-like. I will show an example and you will see, like, if you're familiar with Rust, you will actually feel that it's almost like Rust. This is the first difference. And also Zerosync was using the first generation of StarkProofs, the first one that operates over the 252 bits. And this new project, we are using the new prover using the M31 prime. Those are the main differences. And also feature-wise, we are going further than what Zerosync was doing. because they were doing only the chain header proof, where we also do like the UTXO proving, and also we want to also prove the whole execution of blocks, including proving Bitcoin script execution with a star proof. So it's more ambitious, but this is what we are aiming to do. And hopefully in the coming weeks, we will have something on mainnet, at least for the first part of generating a full recursive proof of the whole Bitcoin chain header. So the flow will be the following. We would actually re-execute the whole Bitcoin chain from Genesis, and we will generate proofs. And we use a mechanism called recursion. And the idea is that you can actually combine proofs. Because the verification of a proof is also a program. So you can verify the verification of a proof. This is why it's called recursion. I won't go into the details, but you can imagine that you have some proofs and you represent them as a Merkle tree. You group them 2 by 2, and then you verify the verification of the 2 proofs, and up to having only one final proof that is the recursive proof. And then you can imagine to have one recursive proof that will be the proof of the whole execution of the Bitcoin chain from Genesis. And then you can use this proof to verify the integrity and to verify that a block is part of the canonical Bitcoin chain with the biggest difficulty. Of course, the way you access the proofs and to know that there is not another chain with more difficulty, it's a challenge, but it's no different than the current thing. If you're connected to some peers, and depending on how you submit those proofs, you could have ways to get them and to have those guarantees. But anyway, the idea would be like you have a recursive proof of the whole Bitcoin chain execution, and then you can verify it almost instantly. So it can be used to improve the IBD process, because there are some problems with IBD. You can be connected to peers that will make you to do some useless work and so on. You can make it a bit more, not a bit more. You can make it more trustless without having to have checkpoints in the code and stuff like that. But in general, you can imagine to be like clients. Maybe it can be interesting to implement this kind of mechanisms in wallets or bridges or whatever, anything that require to have a like client with better trustless properties. Yes, and without having to re-execute all transactions from Genesis. So this is a concrete example on how it looks like in the code, and this is just to highlight that it's something that you can read and write easily. Cairo made it very simple to generate stack proof, so you just write the code. So for example, here you take some inputs like the block date, the time, median time passed, and so on, and you can process transactions. You can implement all the consensus rules of the Bitcoin chain and so on. And from here, you are able to generate a stack proof with that. Another example in the context of Cashu. So Cashu is a Show-Me-Any Cash protocol using Bitcoin and Lightning specifically. So it's not self-custodial. So you have a mint, and you can mint some eCash. Those are bearer tokens, and then you can transact completely private and so on. There is a problematic in the context of Cashu. They want spending conditions. So that you can define arbitrary spending condition. For example, hash time lock, something like that. Not only just signatures with publicly. So initially, Cashu, they implemented something similar to Bitcoin script a bit, like with P2 pay to publicly, this kind of stuff. But there are many issues. First of all, you need to integrate those new stuff and so on. But more importantly, you have a big issue in terms of privacy, because you reduce drastically the anonymity set when you do that, because then, depending on which programs are used and spending conditions, you reduce the anonymity set, and it's bad for privacy. So what we did, and we make working proof of concept that works, you would use Cairo and Stack proofs, and basically the idea would be the following. Alice wants to lock some tokens to a program hash, which will be the hash of Cairo program. In this case, it can be like verifying signature, but it could be anything. And then Carol, that wants to receive the tokens, she will generate a proof, a Stark proof, and then she will send the proof to the mint. And the only thing that the mint will know is that the sender and receiver, they agree, and they don't, and the mint does not know at all what was the program, because what it has is only the proof, and it knows that the proof satisfies the conditions that the sender wanted to lock the tokens with. So it's very interesting. So for now, it's a proof of concept, but we are discussing about maybe going further and at some point maybe enshrine it in the Cashu protocol. So those are ongoing discussions with the Cashu ecosystem. We'll see how it goes. And last example, which is with Nostr. I am very excited about Nostr DVMs, so data vending machines. So the NIP 90, for those who are familiar, the idea is that you can use Nostr as an orchestration layer between customer and service providers. The service providers are DVM, and they can provide different services. So for example, imagine you are a user, you want to have access to a translation service, you will submit a job request on Nostr. Some service providers will say, okay, I can provide you this job for this amount. Then you can pay with a Nostr Zap on Lightning, and then you can access to the service. But then I was thinking that in the future, if this gets adopted, and I hope it will, because I think it's a very interesting way to build permissionless marketplace of digital services. I think one key aspect in the future will be integrity of those DVMs. So I built a proof of concept about verifiable computation on those DVMs. So the concept is that, okay, the DVM would provide the job, but in addition to the job result, it will also generate a Stark proof that will be delivered over Nostr. And then the user could verify instantly the result of the computation without redoing the computation. So it gets the job and the proof, and then it can verify the integrity of the job. So I have a live demo also for that can use any Nostr extension in the browser. And interestingly, we have a wasn't compatible verifier for the Stark proof, so you can easily integrate it in any front end, and then you are able to verify a Stark proof in the front end. And in this case, you will verify the integrity of the computation. I think I don't have time to go back to the demo, unfortunately, but yeah, that was it, unless we want to go into the demo.